let's start with the definition. Exponential growth shows that a quantity is increasing, and we talked about this when we were looking at like tables, right? It increases by the same factor over equal intervals. So like you're multiplying by 3 every time, or multiplying by 7, or sometimes you're dividing by the same factor. In this case, we're always going to call it multiplying by the same factor. When we divide, we're multiplying by a fraction. So I'll show you that in a sec, but I'll let you copy this first. Put this on there too, because this is going to be what we're dealing with today. This is the formula for exponential growth. Okay?
Is that L?
Y equals, no, that's the number 1.
Oh.
This is a 1. Okay? Y equals A times the quantity 1 plus R to the T. And obviously, as with most formulas, each of these things will plug in a number based on what we know. But this formula tells us a lot of things about exponential growth. So it'll tell us about the quantity. Let's put each of them in. I don't like how that looks. Okay. Whatever A is, that's the number that will be the initial amount that you have of something. So that's something that's growing exponentially. So whether it's like population grows exponentially, bacteria grows exponentially, something like that, the initial amount you start with will be that A. Okay, 1 plus R. I'm going to try to erase this because I'm going to rewrite this. 1 plus R. Whatever is in that, this sort of base number, because we'll end up adding 1 plus whatever that growth rate is, we call that the growth factor. That's how much your initial amount is growing by. Okay, the growth factor, you add 1 to the rate of growth. So R is your rate of growth as a decimal. If it's growing by 3%, your rate of growth is 0.03. And your growth factor is 1 plus 0.03 or 1.03.
So 1 plus R is the rate or growth factor?
The growth factor is 1 plus R. R is just the rate of growth. Okay? And then T, what do you think that's going to represent?
A power.
Yes, specifically. What do you think T?
Cube.
Could be. What is T represented in the past when we talked about interest?
Oh, it's like
Time, right? T represents time. So if we're talking about years or months or whatever, you put that time as your exponent, okay? Okay, this formula, you'll have to use this, so just keep it so you can reference back to it as we do some practice. Here we go. Okay, a lot of these are word problems because it has to do with growth of something, so we'll have to pull information from a word problem. So example 1 says, the inaugural attendance at a music festival is 150,000 people.
That's a lot of people.
Yes. It says the attendance, which they're going to call Y, increases by 8% each year after the first year. So it's going up 8% every year after that first year.
Can we write an equation for this?
That's exactly what we're going to do. It says write an exponential growth function representing attendance after T years in this problem. Okay, what did I do here? Nothing. Okay, I'm going to go back. Okay, let's plug in what we know. Do we know A? What is the initial amount here? 150,000. This is our A. Okay, so we can say Y equals 150,000 times 1 plus R. Do we know R? 8%. But remember, we have to write 8% not as a percent, but as a decimal. What's 8% as a decimal? 0.08.
It was like 14%, like 14.
Yeah, 0.14. To the, do we know the time? No, that's what they're going to ask us next. Okay, what I would also want to do is I would want to simplify that 1 plus 0.08. I'm going to write that after I add them. So 1.08. Okay? So my initial amount is 150,000. This 1.08 is what we would call our growth factor, right? That's how much this is growing each year. And then it's to the power of time. We don't know what time is yet, but this is our function. That didn't work. I'll just drop myself.
So then would you just multiply by 1.08 and then add that number on top of the 150,000?
You would multiply it. So first you would do 1.08 to the...
that's right. Wait, but wouldn't you...
Because this is multiplication, right? 150,000 times, and you do the exponent first.
Is that square the final answer?
I was thinking if it was below 1, so it'd be like subtracting it.
That'll come in a minute. All right. So now let's do the second part of this where they actually give us a time. About how many people will attend after 5 years? Well, now we have a t, right? Now we have a number that we could plug in for t. So, yeah, 5. We'd say y equals 150,000 times 1.08 to the 5th power, right? Because now we can plug in 5 for t. When you're doing this, be careful. We talked about this last week. Which operation do you do first?
1.08 to the 5th
Yes.
power.
You must do this 1.08 to the 5th power first. You have to do the exponent before you do the multiplication. So, hold on. If I put this up here, 150,000... 1.08 to the 5th. Okay, first we're going to do 1.08 to the 5th. 1.08 to the 5th. Remember, to do an exponent on the calculator, you use the little caret button to the 5th. So 1.08 to the 5th is about 1.4692 blah blah blah, and then we multiply that by 150,000, and we get that y equals 220 399.2115 whatever. So approximately how many people will attend after 5 years?
How's y is a set of coordinates?
220,339.2.
Yeah. So for sure I would get rid of the decimal. So I would say about, maybe we could say about 220,400. We could say maybe, right? 399 is pretty close to 400. They said about, so we can estimate. So about that many people after 5 years, if it's growing at that rate of 8%, that's how many people would be there after 8 years. Or 5 years, sorry. 220,000.
How come
400.
Yes.
Yes.
Answers a set of coordinates?
So basically what it's saying is when t is 5, y is 220,000. So it is.
Year 5.
Exactly. It's going to be way up there. Yep, you got it. All right. Now, exponential decay, what do you think is going to be the difference here?
It's going to be falling.
It's going to be falling, yes. Whatever you have, your initial amount is going to be decaying at an exponential rate. So here's the definition. A quantity decreases by the same factor over equal intervals. So you'll, instead of increasing 8%, you'll be decreasing by a certain percent. Instead of adding to that one, instead of adding your rate, you would subtract your rate because it's decaying. So here's our exponential decay function. Notice the difference is right here. Instead of 1 plus r, we're doing 1 minus r. So minus that rate of decay, of change. Okay? Everything still means the same. A is your initial amount. R is your rate of decay. T is time. The only difference is that because it's decaying, you're subtracting R. Okay? Okay, this is slightly different, and you have to think a little bit more with decay. The decay factor is 1 minus the rate. It's really easy to see like the growth factor because you just add it and it's like right there. It's literally in your equation. But you have to think about 1 minus the rate to find the decay factor. So just think about that when you're asked about it on homework. You have to actually do the math. Okay, are you ready for me to move to the next slide? Yeah. Okay, so part of this is going to be asking you, is this little table or whatever, does it model exponential growth, exponential decay, or neither? So if it's linear, it's not exponential growth or decay. If it's growth or decay, you're going to say which one it is and why. So let's look at letter A. We've got this little chart. First, we check to see that x is going up by equal intervals because that's part of our rule. Is it going up? Yes, it's going up by equal intervals, in this case 1. And then to see if it's exponential, we need to be multiplying or dividing by the same amount. Are we?
Yes.
Yes. Now, technically, and this is what they're going to ask you to do on your homework, everything is by a factor. So we're always multiplying by something. Now, you and I would say to each other, what are we doing here? Dividing by 3. Is that the same as multiplying by 1/3? Yes. What's 270 times 1/3? Right. Cross simplify 90. So what I want you to say, because technically the definition of exponential growth or exponential decay is you are always multiplying by the same factor. So we don't ever say you're dividing. We're always multiplying. And when we divide, we're multiplying by a fraction. So all you would say here is this is exponential growth or decay? Decay, because it's going down, right? You're going down. So decay. And you would say by a factor of what? 1/3. So that's all we're doing. So just keep that in mind.
Big ideas, but for the 6 way, just say decay by a factor.
Exactly. You'll say decay by a factor of 1/3, meaning we're dividing by 3.
Do we have good ideas today?
Yes. Okay, let's look at the next one. You ready?
Say decaying by a factor of 3.
No, because by a factor of 3 means we're multiplying by 3.
Oh, and
But-
then the fraction needs to divide.
Correct. Bingo. Fraction means divide. Let's look at this one. Growth, decay, or neither. Okay, first, is x going up by a constant amount? Okay, good. So then we can continue. This is check. What about this? Is this exponential growth, exponential decay, or neither?
Growth.
Growth. How do we know?
It goes up constantly by 2.
Very good.
Multiplies by 2.
Very good. We are multiplying by 2, and that's always it has to be a factor. We have to be multiplying. So we would call this exponential growth by a factor of 2. Because it's going up. So if it's decay, you're always going to have a factor that's a fraction. If it's growth, you're always going to have a whole number factor. If on the homework you get something that is not multiplying, so if you're just adding, if you're going like plus 1, plus 1, plus 1, is that exponential growth? No. So you would say neither. Okay? That's linear. Okay, let's look at this. This is another thing it likes to do. Does it represent growth or decay? And then you're going to find that growth or decay factor. So you're going to find R, the rate by which it's increasing or decreasing. Let's look at an example. All right. Y equals 5 times 1.07 to the t. First of all, is this growth or decay, and how do you know?
It's
growth because the number inside the parentheses is positive.
Very good. Okay, because it's bigger than 1.
Yeah.
Because it's bigger than
yeah,
1, but
that's right.
your thought process is correct. This is the number that matters to tell us whether it's growth or decay. If it's growth, it will be bigger than 1. Is this bigger than 1? Yes. Now, it asks us to find the R, meaning what are we adding? How much is this growing by every interval? What do you think? 0.07. R is equal to 0.07. It's however much bigger than 1 that number is. And this is 0.07, bigger than 1. So easy to see on growth, right? Don't get confused on decay. Poor Hemplo.
Wouldn't it be like it could be like a negative one?
It won't be a negative, but it'll be less than 1.
Okay, so it could be like what, 4?
Yeah. Okay, look at here. Here we've got a function, f of t equals 0.2 times the quantity 0.98 to the t. Is this growth or decay, and how do you know? Gwen? Yeah. Very good. It is decay because that number inside the parentheses is smaller than 1. It's not negative, but it's less than 1, meaning it is decaying over time.
And you multiply it by 0.2, correct?
Okay, very good. Yes. The way that we find that rate is we do 1 minus 0.98. So by what rate is this decaying every interval?
1.98.
0.2. Remember that we said that decay is equal to this. Right? To find this value or the decay rate, we have to do 1 minus 0.98. So how much is this going down by each time? What's 1 minus 0.98? 0.02. Yeah. So this is a 2% rate of decay, right? Because it's 0.2 less than 1. Does that make sense? Decay is more difficult to see. You have to actually think about it a little bit. Growth is easy. You just look at how much bigger it is than 1. But decay, you have to subtract it from 1 to find your rate. Okay? All right, let's look at another example. All right, here we go. Compound interest. So we did simple interest a long time ago, didn't we? You did it in 7th grade, I think.
That was the one thing Mr. W did do well, simple and compound interest.
Great.
Because that was actually going to be applied in the real world.
Got it. Okay. All right, compound interest. Let's look at it. Will be a formula. And it will be very similar to growth. Exponential growth. So what compound interest is that you're earning interest on both the amount of money you deposited initially and on the interest you made on that money. So you earn a lot of money fast with compound interest. It's a huge return.
Mrs. Lerzio.
Yes.
Pop quiz. If you have $1 million and you have 5% compound interest each month, how much will you make after 2 months?
I have no idea.
F.
A lot. F.
7.
Total F.
7.
It'd be a ton. That'd be I'd take that deal. Okay, here's the formula, you guys. It looks bad. It's not that bad. It's really not. We're going to talk about what each of these mean. So y equals P times the quantity. That's a 1. Again, this is a number 1, not an L or anything. 1 plus R over N times N to the T. Now, some of these we know what they mean. R is going to be your rate. T is going to be time. 1 is going to be 1. P is going to be principal. So it's what you deposited. All right, but let's put them all down. Okay, Y is the total balance of your account that includes the interest and the principal. So the total balance of the account after a certain amount of time. P represents, as we said, the principal amount. So whatever you deposited, whatever Zegan said, what did you say, $1 million, $5 million? Okay, whatever you deposit to start. R represents your interest rate written as a decimal, always as a decimal. It'll give it to you as a percent. You have to change it to a decimal. Okay. N will represent the number of times they compound the interest annually. So if it's compounded annually, that's once a year. N would be 1. If it's compounded monthly, what would N be?
12.
12, because there's 12 months in a year. If it's compounded quarterly, what would N be? How many quarters are there?
4.
4. It would be 4, because 4 times a year, every quarter.
Yay, water.
All right? And then T will represent
The
time. And there's a stipulation with interest. It always has to be in years. Time will always be in years.
So if it gives you like 365, like 367 days, would you just put 1 and then that
Point.
fraction?
Yes. Yes. It won't give you that bad. It might say 6 months, and then you have to say 0.5 or something.
Like 1/2.
Yeah. Yeah. So just be careful. Be wary of months. If they give you months, make sure you change it to a fraction of years out of 12. Okay. Let's do an example. If you deposit $100 into an account, earning 6% annual interest, compounded monthly. This is our keyword. When you are seeing that interest is being compounded, use compound interest formula. Okay? Here's what it asks. Write a function. So first we're going to write the function representing the balance after T years. And then what do you think they'll ask us next? They'll give us an amount of years. All right. Let's start with our formula, this little guy, and let's plug in what we know. Let's plug in what we know. Okay, do we know P?
Yes.
Yes. What's P?
1 on 100.
100. That's our principal amount. So we'll be able to plug in 100 for P.
Oh, we can plug in the N because we know that it's monthly.
Monthly. So N monthly, what would N be? How many times in a year?
12.
12. So N is 12 because that's always the number of times it's compounded per year. If it's compounded every month, it's compounded 12 times a year.
Wait, what's R?
What is our?
Wouldn't it be 0.6?
That's your rate. It is your interest rate. So we know that our 6%, we'll write that as a decimal, 0.06. From here, the only thing we don't know is T, and that's fine because we're going to leave it so that we have our function that we can just plug in. Let's plug all these numbers in and get a nice, neat little function. Y equals 100 times the quantity 1 plus 0.06 over 12 to the 12t. Now, what you're going to want to do, and we'll do this, get all this down to one number. Okay, so let's do 0.06 divided by 12.
Is that going to be 24?
It's tiny. It's 0.005.
Oh, I was dumb.
So what's 1 plus 0.005? Yeah, so let's put that in here. Okay, 1.005. Here's our function. This is as simplified as we can get it. Can we multiply these two together first to simplify this more?
No, don't you have to do 1.005 to the 12?
Yes.
Yes.
So no, we cannot multiply these two together. Because of the exponent, we can't multiply. So don't be tempted to do that. That's not simplifying. That's getting it wrong. Okay, this is our function. So that represents the balance after T years. Now, how much money do you have after 2 years? What are we going to do?
You plug in 2
Plug in 2 for T. So up here, instead of T, let's plug in 2. 12 times 2. All right, so we're going to do 1.005 to what power?
to the 24th.
To the 24th power. which gives us 1.12715, etc. Oops, 27. And then we'll multiply that by 100, which gives us 112.7159 ... Okay, remember with money,
They cut it off at the hundreds place?
yep, cut it round to the nearest hundredths place.
How are we gonna write that?
So
on-
7.
So, how much money do you have after 2 years?
$112.7.
0.72. Round that 1 up to a 2 because there's a 5 next to it. So after 2 years, you've made $12.72.
Wouldn't you round that 5
Wouldn't
up
it be
to a
100
6
now?
because it's a 9 and then that 6? Oh, wait a minute.
No, only look at the place and to the right.
Wait, wouldn't that be 112?
Yeah,
That's what it is.
that's what I said.
You said 12.
Oh,